warm up to help refresh our brains on the graph of y equals natural log of x. So yesterday you got to refresh your brains on inverse trig. Today you get to refresh your brains on natural logs and regular logs too. So everyone, I'm seeing every single group got the domain and range correct, so well done. I'm just going to do a quick check. Yes. Did you all get 100%? Yes, we did. But yes, you did. Yeah, they look fantastic. So we won't spend too long on this since every single group got all perfect answers. The domain of the natural log of x, there is a vertical asymptote here at 0. So what happens is the graph just continues to go down here forever, but it will never actually cross the line x equals 0. So the domain of a natural log is from 0 to infinity. And it would be an open interval because you can't include the 0. There's an asymptote there. Speaking of that, someone asked me yesterday about last night's homework. They asked you for the range for inverse tangent. And I apologize that I had put them in brackets, but inverse tan has asymptotes at negative pi halves and pi halves. So you can't include the negative pi halves and pi halves. You have to do parentheses, not brackets. Okay? So if you got that wrong, that's why. It's because it needs to be parentheses and not brackets. So I apologize for that. All right. So range. So range, those would be all your y values. Well, we're obviously going down to negative infinity. If you look at your calculator, calculators with natural logs, it makes it look like it flattens out. And so a lot of people think natural log has a horizontal asymptote, but it doesn't. It always grows. It just grows really, really slow. Now, we're going to take 2 seconds and explain why. If I have the graph of y equals 3 to the x, right? Just so you know, 3 to the x and log base 3 of x are inverse functions, right? E to the x and natural log are inverse. Any log and exponential with the same base are natural inverse functions. So, which means their x's and their y's swap, right? We talked about that a little bit yesterday. So 3 to the x, let's think about 3 to the x. So 3 to the x, 3 to the first is 3, right? 3 to the second is 9. There's Blake. Welcome. Okay, that's okay. Do you want to just join those ladies over there? Okay. So 3 to the third is 27. 3 to the fourth is 81. When you get to x equals 5, 3 to the fifth, you're all the way up at 243, right? So any exponential grows really fast, right? So you're at the point 5, 243. Now I want you to reverse it and think about log base 3. Log base 3 means that the log base 3 of 3 is 1. It's the reverse. The log base 3 of 9 is 2. The log base 3 of 27 is 3. So if you go all the way out to x equals 243, your y value is 5, right? Because the y value is the exponent. So you're growing, but you're growing really slow. Does that make sense? So logs will get to infinity. They just take a really long time to get there, right? But they'll get there. They're slow and steady, right? Okay. So the range, all that being said, the range is negative infinity to infinity. All right. The limit as x approaches 0 from the right. So from the right, what are we pointing to? We're pointing to negative infinity. From the left, what's the limit? Doesn't exist because there isn't even graph there, right? D, N, E. I'm going to talk about that. I didn't talk about that in first period. I'm going to talk about it right now, before I forget. So, okay. So, y equals ln x, and we're going to break this down on the next slide, but just so you know, what's the base of this? e, right? This is base e. This is your exponent. The natural log, I'm going to write it like this. So ln of x equals y. So that means e to the y equals x. When you have a natural log, if you want to write it in exponential form, this base to this power equals this guy. E to the y equals x. I want you to think carefully. Can you take e? What's e? Roughly. 2.7. 2.7. You're close. You have the 2, right? Okay. So e is around 2.7. Let's just say e is around 3, right? So if e is around 3, can you take 3, raise it to any power in the whole universe, and make it become negative? No. Nope. What about like 3 to the negative first? That's 1/3, right? No matter what exponent you raise it to, if you have a positive base, your answer, this guy right here, has to be positive. Which is why your natural log and all of your logs that have positive bases are only defined for positive values of x. Plus 2. Because there's no way to raise a positive number to an exponent and make it negative. Okay. So, and just, you know, we would never have logs of negative bases because they're just all wonky. Like, the graphs are insane. Anyway, think about all the real numbers having to decide, is this real number even or odd? Like, if I raise -2 to the 3.817654, is it going to go negative or is it going to go positive? Right? How do you know? So anyway, so when you graph like logs with negative bases, you just get a bunch of nonsense. Okay. All right. So that being said, that's why log is only defined for positive x values. So, and then the limit, of course, since the limit from the left doesn't even exist, the limit itself doesn't exist. And then the limit as x approaches infinity, we all know is infinity because we're going up to infinity. All right. I want you in your heads to have the graph of ln x in there. It doesn't have to be perfect. It can just be a swoosh. A swoosh is okay as long as it's a fairly decent, like if we're talking about ln x, in your brain, you should be able to like picture that, right? It doesn't have to be perfect. You don't have to know all these ordered pairs or anything, but you should know at least basic shape and that it only exists for positive values of x, right? And how it goes. This is going to help you, especially in the next chapter, when we have to start doing all kinds of breaking the function down and sketching it and analyzing it. So once we have to start doing that, having a general idea of the graph will come in very handy. So this graph should be somewhere in here, okay? In your family, do you have like in your head, do you have like a family of functions graphs of like all the different function families? I know you guys did this, right? Didn't you do function families? Kind of, right? Like knowing the general graphs of all of your function families. That's algebra 2. I heard parabola. All right, good. Okay. Oh. Having a lot of technology issues today. That's all right. Okay, we're still in pre-calc mode. We haven't done any calculus yet. Yay, pre-calc. So we're going to review properties. You should know all of these, but we're going to review them anyway just to make sure, just in case you forgot them, right? Oh, did I never show you the starting page? I'm so sorry. It's because I skipped that first warm-up because of the internet issues. This is 3.6a. 3.6a is derivatives of logs. Tomorrow we're going to do 3.6b, which is called logarithmic differentiation, which sounds the same, but it's not. Friday we do 3.7, and then we're skipping 3.8. we might even be skipping 3.9 and just jump into 3.10. I'll have to look and see. We will do 3.8, but we're pushing it to after the test. It's not on your test. I'm going to say it's a week from Tuesday. It's the Tuesday before MEA. It's the Tuesday before MEA. Okay, so remember that a logarithm is the inverse of an exponential. So if y equals a to the x, can we write this in logarithmic form? Log base something of something equals something. Take a second in your groups and see if you can figure out how to write y equals a to the x in logarithmic form. All right. Okay, so the nice thing about logs and exponentials is the base stays the base. So the base of the exponential, which is a, is also the base of your log. So the base of your log is going to be a. The whole log is always equal to the exponent. So a log, the entire logarithmic expression, is an exponent. So I always set it equal to my exponent, and then I just fill in with the other stuff. So when I am doing logs, my brain is always thinking this way. So if I see a log, my brain always thinks this base to this power equals this. A to the x equals y. A to the x equals y. My brain makes this little circle in my head, and that's how I'm thinking. Every time I'm evaluating a log, that's what I'm thinking. So if I see this ln, there is no base. So what's the base? E. This is called a natural log, or log natural, of course, because we'll get it, when we do a Mathematician Monday, we should have, well, no, it was good to do Newton this week, but next week we'll do Napier. Napier's great. He's really interesting. So the person who first, really came up with logarithms was John Napier. And really all he did was he spent most of his life creating tables of logarithm values. And why did he need, or why did mathematicians need logarithm values back then? Because for them, it was the only way to solve, 3 to the x, I can draw an x, 3 to the x equals 5, right? So if it's not 3 to the x equals 9, we know what x is, but if it's 5, we're like, something bigger than 1 and less than 2. We don't know what it is, right? So he created this whole set of log tables, and I'm not exaggerating. When I was in school, that's how we did our logs. We flipped to the back of the book. There was a whole set of log tables, and you just looked it up on the log table, right? So we had the log tables in our textbooks right up until maybe 20, 30 years ago. So anyway, yes?
How do you times a number by itself 1.9 times? What does that mean? Do you know what I'm saying? It's
You're taking 1 and 9/10 of that number, right?
If you're raising it to the 1.9.
Oh, you're doing it to the 1.9 power.
Yeah.
Okay, so then that would be, let's see. How do we interpret that? It's 3 times itself 1.9 times.
That's always been confusing.
Yeah, it was a little confusing. What's fun, do you know how your calculator does logs? How does your calculator compute logs? With what? By pressing enter, it's magic. It has a little magic thing in there. Do you think that your calculator has stored all of Napier's log tables and it just spits them out?
Yeah.
How does your calculator do it? It does it with series. It converts the logarithm function into a polynomial, which is what you're going to learn how to do next semester with Ms. Grunwald. So, yeah, your calculator converts, it does all the functions where you can just type in a number and hit a button like sine, cosine, tangent, log, e to the x, right? All of those, the calculator does all of those with series. So you're going to get to learn how to write all the series that generate those functions. So it doesn't do a graph. Your calculator does a series. You're going to learn about it when you learn series. So just know when you learn series, not all, but one of the main uses for series is the only way that your calculator or your computer can calculate values of those types of functions like logs and trig and inverse, all that kind of stuff. So it does it all with series. All right, that was a long explanation for, let's get back to what ln e is. Okay, so ln, so let's just write here, ln e is the same as log base e of e, right? So whenever you see ln, there's an invisible e down here. So the base is e. E is our, we use base e for the vast majority of problems in this class. Why do we use base e and not base 10 or base 3 or whatever? Because e is your natural base for all exponential growth and decay, right? All populations grow or decay with based on an exponential function that is base e. E is the basis for all natural exponential growth and decay. And when you get to, I don't know if you have to wait until you get to series. It might be when you get to series, you will derive E. So I don't know. I don't know if Ms. Grunwald will make you derive E. We derived E in my class, but it's not necessary. But it's kind of fun to understand where did this 2.71828 come from, right? Someone just pick a random number and say, hey, that looks good. I mean, there's a reason for it, right? So how does it get derived? So you have, again, that would be like in the series unit. But anyway, we'll derive E. But yeah, E is that natural base. So it kind of comes out in nature. And all of your derivatives and integrals are base E. So if you have a log of a different base, what you actually do is you convert it to base E, and then you do your derivative. But we give you a formula for it so that you don't have to actually do the conversion. You just spit out some stuff and it works. So anyway, so here's the thing. Log base E of E, if I set this equal to like some question mark, what you're asking yourself is E to what power equals E? 1. So the natural log of E is 1. If I asked you for the natural log of 1, then you're saying E to what power is 1? 0. Natural log of 1 is 0. Log of any base of 1 is 0, right? Anything with 0 is 1. All right, let's see how well you remember your properties from last year. The natural log of 8, remember that a whole log is a what? It's an exponent. Logs are exponents, right? So the properties of logs are very similar to the properties of exponents. So when you are multiplying two bases with exponents, when you're multiplying them together, what do you do with the exponents? Say I have 2 to the 3rd times 2 to the 5th. That equals 2 to the 8th. You add them, right? Everyone's thinking about it. It's true. Okay. All right. So same thing here. The natural log of A times B is ln A plus ln B. So when you multiply your arguments, you can break up the log and say you're adding the log. What about when you divide your arguments? You subtract the logs. if I take something like 2 to the third, let's say that's a 3. 2, that's a 3. 2 to the third to the fourth power, is that 2 to the 81st? 2 to the third to the fourth? What is it? 2 to the 12th, right? So when you raise an exponent to another exponent, you're multiplying your exponents, right? Okay, same thing with logs. If I have an exponent to another exponent, I multiply the log by the exponent, which really means just you put the exponent in front. You're multiplying your exponents. There's one more property that we use a lot in this class that I don't have on here, but we're going to write it, so we're going to put in number 6. I was really surprised. No one in first period knew this one. And Mr. Thomas, who is our former calculus teacher, came in for a visit during first period, and he was shocked that nobody knew this one. So I was quite surprised. I'm very curious to see if you know this. The log base A of B equals ln of something over ln of something. Anyone know what it is? It is. It's ln of B over ln of A. That's called your change of base formula, because back in the day, which wasn't that long ago, if you needed to do a log base 7, there was no such thing as log base 7 on any calculator. All we had when I finally got like my fancy scientific calculator, it had an ln button, right? And actually some calculators had both an ln and an log, but log is base 10. So you could only do natural base E or base 10, and that was it. So if you had to do a log base 7, what did you have to do? You had to convert it to either base E or base 10. So this was how you convert it. It's your change of base formula. So log base A of B is natural log B over natural log. It's also, just so you know, you can actually convert it to any base. Like this is actually the same. This and this are the exact same thing. They'll give you the same answer. So you can convert to any base you want. So that's called your change of base formula. But this is the one that we're going to use because log base 10 doesn't help us at all. All right. Did you learn this last year? I'm so curious. Okay. Jennifer says she did.
I definitely do not remember that.
Definitely do not remember.
Gronkowski
Gronkowski mentioned it. What about Keki? Nice. You guys are so hard on Mr. Keki. All right. Okay. Now there are some gotchas. All right. These are what not to do. So anything that's here is bad. So make sure you know, do not do this. All right. This is bad. I get nervous when I show you something not to do. It's kind of like when, how do you say it? Like if you have a 2-year-old, right, and the 2-year-old is running, you never say, don't run, don't run, don't run, because what do they hear? Run, 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 right? So you never say what not to do. You say walk, 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 right? You tell them what to do, right? So here, I'm worried I'm going to say, don't do this, and then it's going to stick, and you're going to do it, right? So, but I need to show you because so many students do these, and they're bad. So you need to know these are bad, all right? So I'm going to make this really big. So ln A over ln of B does not equal ln A minus ln B. When you divide the logs, you're just dividing the logs. Actually, what does ln A over ln B equal? It equals log base B of A, right? It's a change of base. It's not this. Notice for these, everything you're doing is to the argument. Argument multiplied, argument divided, argument raised to a power. It's not whole logs being multiplied or whole logs being divided, right? It's just the arguments that are being multiplied or divided. All right. This is a biggie. ln of A plus B, what do you think people think it means? It equals ln A plus ln B. Does ln of A plus B equal ln A plus ln B? No, because what does ln of A plus ln of B equal? ln of A times B, right? Okay, so be careful. ln of A plus B is just ln of A plus B. There's nothing you can do about it. So if you have the natural log of x plus 2, welcome to the world of natural log of x plus 2. There's nothing that you can do to break it up. All right? Okay. ln of A, the whole log to the B power, and I'm going to make this really big, is not B ln A. When you're raising the entire log to a power, it just means ln A times itself B times, right? So that's not, you can't just put the B out front. It's ln A. So, oh, and a little shorthand, little notation. A lot of books don't want to have to take the time to put parentheses and like put an exponent out here. So if you ever see the squared in between the ln and the A, that means that this and this are the same. So if it's kind of like this, it's like the same as, it's like if you have sine of x quantity squared, we write that as sine squared, right? So you could do the same thing with logs. So if you ever see the squared here, this means this, not ln of A squared. If they want ln of A squared, they'll say ln of A squared. All right. That's a lot of pre-calculus. Ready to move into calculus? We're not ready yet. There's still a little more pre-calc to do first. Okay. Diríamos. Okay, that's okay. Okay. Oh, I can't use this. That's right. It only works here. Okay. So we're going to practice our log properties by condensing and expanding. When you condense with logs, it means you write this whole big expression with one log, no coefficients. All right? So I want you to take them in your groups and see if you can write this whole big expression as one log with no coefficients. Just do it on paper. And then for this guy, when you expand, you're breaking up the logs. So you write it as multiple logs, right? Okay. So go ahead and get to work on that. I'm going to pause this for a minute. And I have to do it over here. Done. All right, so for the first one, here's my advice to you. Whenever you have a bunch of logs, anything that's being subtracted goes to the bottom. Anything that's being added goes to the top. Doesn't matter the order, right? Whatever's being subtracted goes to the bottom. Whatever's being added goes to the top. So you have an x, you have an x plus 1, and then this x minus 1 up here. What do I do with the 2? Becomes an exponent, right? 2 becomes an exponent. So this is ln of x times x minus 1 over x plus 1 squared. Yes, you can. Even though I'm adding what? I didn't hear what you said, but I'm assuming it's right. Okay. You're good? Okay. All right. Let's expand. ln of x times z times the square root of z plus 2. That's ln of x plus ln of e plus ln of z plus 2. All right, there's one more thing I want you to do before we say we're done with this one. What's the ln of e equal to? 1. And what can I do with this root? Put a 1/2 in front. of everything that we just did on this entire screen, which of these things is the most important for you for your derivatives tonight? The most important thing you can learn of everything that we did is this root. You could just put it as a 1/2 in front. Because doing a derivative of a natural log of a root is kind of a big, ugly mess. But if you just put the 1/2 in front, then it's just a natural log of a polynomial. That's super easy. All right, so anytime you have a root, you're going to put that exponent in front. And I will tell you right now, you're going to be expanding all the time. You'll almost never condense. But the expanding is a constant. That's going to happen on almost like every problem. Except the first few, because I'm going to start you easy. Okay, are we ready? All right, it's time to actually do some calculus. 31 minutes of pre-cal. Here we go. Okay, so we're going to play name that derivative. We're really not going to play, but I want you to mentally play this game. So here's what I have given you. In this table, if you can see this, can you see this in the back? Kind of? Yeah? Okay. So this column right here, those are your x values. These are natural log of x. This is the derivative of natural log of x. So if x is 0, then natural log is undefined, so the derivative is undefined. But if x is 1, the derivative is 1. If x is 2, the derivative is 0.5. If x is 3, the derivative is 0.33333333. Now what I want you to do is, without speaking, mentally see if you can figure out what the derivative of y equals ln x is. And my hint to you is if you can't figure it out, mentally convert those decimals to fractions. So I give you 10 seconds. See if you can figure it out. All right, that was more than 10 seconds. So Keegan, how are you?
I'm great. How about you?
I'm doing great. So do you have an idea for what the derivative of natural log x is? All right, walk me through your thinking. What's 0.5 the same as?
1/2.
What's point? So if x is 2, the derivative is a 1/2. If x is 3, the derivative is a 3rd. So it has what? If x is 4, the derivative is a 4. It is 1 over x. Woo, you win. Yay. Okay. All right. Very good. So if y equals ln x, then y prime is 1 over x. Ah, okay, so Ryan's getting ahead now and saying, yeah, but you're not going to ask us the derivative of ln x 20 times, right? So instead of asking you the derivative of ln x over and over, we're going to ask you the derivative of the natural log of 6x squared plus 5. So I'm going to show you a formula in a second, but I want to see if you can figure this out using chain rule. All right? Just take a second. Good. What do you think I'm going to put 1 over for this to start this derivative? You would be correct. But that's not an x. That's a whole expression. What am I going to have to multiply by? 12x, the derivative of the guts. Does that make sense? So if I cleaned it up, it would actually be 12x over 6x squared plus 5. So, So if I have a log, and it's not just x, it's like stuff, right? A log of stuff, or a log of guts. And the derivative looks like it's d guts over guts. Yeah, it's just d guts over guts. So in general, here's your form. Oh wait, that was very anticlimactic. Hang on. Here's your formula. Okay. So in general, we're going to go back to that u notation. The derivative of ln u. Remember, u represents any expression of x, right? So it can be, 5x squared minus 3. It could be, x to the 2/3, whatever. U represents some function of x. So what is the derivative of ln u? It's u prime over u. It's d guts over guts. U goes on the bottom, its derivative goes on top. Now, we haven't talked about logs that aren't base e. The formula for the derivative of log base a is u prime over u ln a. It's almost exactly the same as u prime over u. By the way, if I wrote this as u prime, what's the base of a natural log? E. If I wrote this as u prime over u ln e, would that be wrong or would that be okay?
That would be okay.
Why?
Because it's mathematically.
Yeah, because ln e is 1, right? Okay, so it works for e as well. It's just that nobody writes the ln e because it's just 1. All right, so how did we come up with this form? Does anyone want to know how we got this? Why do we have to divide by ln a? Or do you guys not care? Like, it's okay if you don't care. I won't show you. Do you want to see?
Yeah.
You'd like to know? Okay, good. All right. Where's my expand page? Okay. No, it wouldn't be there. It's always in the center. All right. So here's what I'm going to do. I'm going to move this out of the way and just show you over here. All right. So suppose y equals log base a of, let's just do x for now and keep it simple. Log base a of x. So I mentioned a wonderful formula when we were doing our properties. I added a 6th property, which is called change of base. So log base a of x is the same as what over what? Ln x over ln a. So this and this are exactly the same. All I have to do is write this as 1 over ln a times ln x. What is ln a? It's is it a variable? Is a a variable? It's a constant. It's a constant. At 1 over ln a, this whole big thing right here, that's just a great big coefficient, right? It's a number. Coefficient, right? It's a number. A is a number. So the derivative of log base a of x is the same as the derivative of ln x over ln a, just writing the 1 over ln a in front. So it's really just 1 over a times the derivative of ln, or 1 over ln a times the derivative of ln x, which is u prime over u. Okay? So all you do is you have to divide by that ln a because that's what converts it to the natural log. So this and this ln a is just so that you can convert it to the natural log derivative. All right, so I have 4 lovely problems on the board. I want you in your groups to put these on your whiteboards. I'm going to give you about 5 minutes to do all 4 of them. Starting now. The first 3 are pretty straightforward. D guts over guts. So when I do a derivative of a log, I always write a fraction bar and then I put my guts on the bottom, and then I put the derivative on top. I always write the guts first. So guts go on the bottom, derivative goes on top, done. Okay? For the next one, guts are secant. What's the derivative of secant? Secant tangent, right? So you have secant tangent over secant, which I simplified to tangent. But, if you did, that's okay. All right, so, which I think most of you did, so well done. All right. For the next one, what's the derivative of cosine? Negative sign, right? So you'd have negative sign over cosine, but you also have to divide by ln 6, right? So negative sign over cosine ln 6, which you could write as negative tan over ln 6, but you don't have to. The last one, there are two roads that you can travel down for the last one. One is the long and winding road, right? And the other is the nice, easy shortcut road. We all want to learn how to travel down the nice, easy shortcut road. So the advice I have for you is whenever you have to take a derivative of a log with a root, always write your exponent in front first. Because if you don't, the log becomes a lot more difficult and the simplifying is going to be rather tricky. So if you just rewrite your f of x for this guy as, what's the exponent? 1/3, it's a cube root, 1/3 times the log of 5x minus 7. I didn't give you a base. What's the base? 10, right? LOG is called the common log, and it's base 10. So, all right, so now this is super easy, right? So your answer is just, so your f prime is just 1/3, and then guts go on the top, the bottom, derivative goes on the top. Don't forget to divide by the ln of the base. And I was telling a group the other day, so this answer, I was telling a group the other day, meaning like 2 minutes ago, that you have to be careful with your fraction bars, especially on the AP exam. The College Board does not look kindly if you are messy and you kind of like go like this, right? They're going to think that you're doing 5 over 3 times 5x minus 7 and the whole expression's being multiplied by ln 10, right? You got to be very clear with your fraction bars and make sure it goes over the whole thing, or they're going to assume that you mean multiply. So they're real picky about that kind of stuff. And please don't do this. Please, I beg of you, no sideways fractions, all right? Please don't. If you're going to do a sideways fraction, you had better enclose everything that's on the bottom in some sort of a bracket, right? Because otherwise I'm just going to assume it's 5/3 and everything else is going to multiply. All right, so I would just prefer you don't do any sideways fractions. All right. All right.
Aren't the AP graders supposed to assume the best or something?
No, they don't want you to fail. We'll talk about AP grading in a few minutes, or in sometime, but not right now. All right, so on paper, what I want you to do is find these two derivatives. They're almost exactly the same, but I want you to realize that if you break up the log first, if you apply your log properties before you do the derivative is so much easier. It's so much easier. So before you do the derivative, I want you to break up, expand the log first, then do the derivative on paper. So take a minute or two and see if you can do each of these. The second one is just like the first with a very small difference. Okay. The first one, if you break it up, so you get, so the natural log of x to the 7, which you can leave as the natural log of x to the 7. It's really not a hard derivative. But you could also put that 7 in front, right? Make it 7 ln x. Am I going to do plus or minus here? Minus, because we are dividing, right? Yeah. And then what exponent is on the bottom? 1/2. So 1/2 ln 8x squared minus 4x. By the way, did you guys put it together that when you're multiplying, you would be doing plus 1/2, and when you're dividing, you're doing minus 1/2. But if you think about it, really, if you think of this exponent, you could also rewrite this as x to the 7th times this to the negative 1/2, right? And you do plus, and then a negative 1/2, and you get the same thing, right? That's why you're subtracting when you divide. It's just a negative x. It's really multiplying with a negative exponent. Okay, so anyway, so for this guy, we get 7 times the derivative of ln x, which is 1/x, minus 1/2 times, guts go on the bottom, derivative goes on the top, 16x minus 4. I'm going to put that in parentheses, and then I'm going to stop. Done. Yay! Okay, this one right here, what's the only difference between this guy and this guy? The only difference is that this becomes a plus, right? So the only difference, you know what, I'll write it out real quick. So d dx of 7 ln x plus 1/2 ln 8x squared minus 4x equals, bless you, 7 times 1/x plus 1/2 times d guts over x. Okay. All right, we're done with logs, but we're not done with the lesson. Because I decided this morning, and I added these on just like during class, because I've been getting people coming in mornings and afternoons who are having trouble with some of the other derivatives we've done in the last week. So I thought it might be good if we just practice some of these as a class. So suppose y equals e to the 8x squared plus 2x minus 10. Just take 10 seconds on your paper and see if you can find y prime. People are flipping in their notebooks. All right, instead of flipping, I'm just going to tell you, what's the derivative of e to the x? E to the x. This isn't e to the x, this is e to the guts. So when I have e to the guts, what rule do I have to apply? Chain rule. Do the guts change when I use chain rule? Never. So the derivative of e to the guts is just e to the guts d guts. Yes.
Since we were reviewing, how do you think, like, I think it was in 2 days or something, I don't know.
Is it a second derivative with a real complicated implicit differentiation problem?
Yes.
Well, we'll see if we get to that. Okay. So, now, I tacked on an LNE just because we were talking about it during first. Did I have to times it by LNE? No, of course not, because that's just one, right? So really, look. This is what I would expect to see for your answer, right? So the derivative of e to the guts never, ever, ever, ever change for any derivative ever until you die, ever, okay? But you multiply by the derivative of the guts, always. Okay, that's the change. Okay. All right. Any questions on this one? Let's do the same thing where it's not base e. Let's do it where it's base 3. This was the one that you got in the screencast on Friday with the sub that you all loved. No, wait, we were all all right, quiet down. The derivative of 3 to the guts is the exact same thing as the derivative of e to the guts, The only difference is you have to multiply by something to convert it to that natural base. So the derivative of 3 to the guts is 3 to the guts times what? Times d guts, the derivative of the guts. And then in order to convert this to a base e, we have to multiply this by ln 3. Can you distribute this 3 into here?
No.
No. Don't do it. Whenever you have like an a to the guts kind of a derivative, you can always expect there's going to be like 3 parts to your answer. So the a to the guts, the d guts, and the ln. All right, I was asked to do a problem from the implicit differentiation homework from 2 nights ago. Okay. So it's amazing, like Faith and I are on the exact same wavelength here. So this homework, only, 5 questions for the whole homework is like nothing, right? All right, so after working with some students, I realized that these were 5 like really meaty questions. So these questions had some good heartiness to them, right? So yeah, so that's good. Okay, it's good for you, right? If it doesn't kill you, it makes you stronger. So these questions made you strong. Here we go. Quiet down. Quiet down. For the first term, what rule do we have to use? Product rule, right? Okay. Okay. So the derivative of x is, this is all with respect to x. So the derivative of x is 1 times y plus x times, what's the derivative of y? dy dx, right? Okay, so that's that first term. I'm going to go and just expose the whole thing. So 1 times y plus x dy dx. The derivative of 5e to the y is 5e to the y. Guts never, ever, ever, ever change, right? But then you got to multiply by d guts. What's the derivative of y? dy dx. What's the derivative of 5e? What is 5e? It's a constant. If there's no x, there's no variable, it's a constant, right? Oh, Keegan, that was you? Yeah. Okay, well done. All right. Yeah, the derivative of 5e is 0. So don't let them, like, they're just trying to, mess with you, okay? Derivative of 5e is 0. Now, once you got this, I would solve for dy dx. So if I have to find a second derivative, I'm going to solve. You can do it by doing a bunch of product rule involving your differentials, but I would prefer to just solve. So I solve through dy dx by moving the y over to the other side and then doing, what's our favorite F word? Factor. Factor the dy dx out and then divide by those other 2 things. So there's my dy dx. But it didn't ask for y prime. It asked for y double prime. Yay, we get to do a second derivative. What rule am I going to have to use? Quotient rule. Okay. So for quotient rule, okay. So for quotient rule, the derivative of the top, the derivative of negative y is negative dy dx, right? So you get negative, it's okay. The derivative of y is dy dx, right? So the derivative of negative y is negative dy dx times the bottom minus the top times the derivative of the bottom. Well, the derivative of the bottom, the derivative of x is 1. The derivative of 5e to the y is 5e to the y times dy dx. All over the bottom squared. Follow your quotient rule. Now, you can't leave dy dx in an answer. So I got to replace dy dx with something. What is dy dx? It's this, right? wherever I have dy dx, I replaced it with negative y over x plus 5e to the y. All right, this is like easy peasy. Come on. It's like nothing. Yes.
It's not hard. It's like
What negative 1. Oh, look, you plug in your y right away. Yes, you could. Yeah. Okay, so the reason I had done all this, in all honesty, first period, was because I didn't realize that they asked you to plug in a number. So I thought the question was, what's y double prime? So I was ready to stop here and type this giant thing in. And then everyone said, no, it's at x equals 0. It's at x equals 0. So then we are like, oh, okay, let's back up. So yes, you could have plugged in the x equals 0 like right away, but you got to find y first. Yes, Nisha.
So I did something else. Would it be okay to just times the 1 prime by itself? Because on the other side, would you just take dy dx of dy dx and just multiply like negative y over x plus 5 to the y by itself? Because did you get 1 over 25d squared at the end?
I did.
Okay.
I have to look and see what you're doing. I don't know if I can follow it verbally. Okay, so the question is, if I know x is 0, how do I find my y value? What do I use? The original function, right? That's how you get any y value, is you plug in your x to the original function. So when you plug in x to the original function, you get that equation. Hi, Mrs. Elsker. Yes. Oh, okay, I will. Got it. All right. You're welcome. Okay. So anyway, so you plug in an x into the original function and you get the 0.01. So then you go down to your second derivative and you plug in the 0.01 and you clean it all up and you end up with 1 over 25 squared. Okay, so like in just a minute we'll okay. All right. Hey, any problems, fair game, right? Right? Okay, so anyway, so that's that.